Yeah, I was just curious with the second problem, there is no image being passed, so the function that is being called does not have any.
Oh yeah, don't worry about it. I fixed it last night. I think Andrew didn't update it. That's just it.
So
Okay.
she was concerned about something that was not ready to use, but was fixed last night. Okay, so let's continue. We've been talking about good ways to reform an image into a linear combination of basis images. And one of the major objectives was to allow shift invariant linear operators to be applied efficiently. And we saw that that would happen because for those operators, the sinusoids, the Fourier basis functions, were such eigen images. And so transforming the image into the coefficients and then operating on those coefficients and then transferring back into the image would be an efficient way of applying a shift invariant linear operator. And now we're going to start talking about actual shift invariant linear operators, okay? And we're assuming that we have the Fourier basis functions. The form in which the program that you're working with is the amplitude phase form of the coefficients. But we saw that the theory was perhaps particularly well understandable in terms of the complex exponential form, e to the I theta form. And that could also be understood in terms of the sine cosine coefficients. We also saw that when we decomposed an image into these coefficients of sinusoids, many of the high frequency coefficients, that is to say the k over capital N frequency, at frequency such that k over n was large, at those high frequencies the coefficients could be expected to be very small because all images have somewhat limited resolution. Essentially, why do images have limited resolution? Not because scenes have limited resolution, but because cameras always damp out the highest levels of detail. We'll see why that happens also. But anyway, the result is that you really only have to operate frequently on only a small fraction of the frequencies when you're doing these operations. This last bullet notes that the image is a mapping, is a function on the Euclidean plane, or in 3D, the Euclidean three-dimensional space. Turns a function, an image, in that space to another image in that space, if you're doing a shift invariant linear operator. But there are other spaces in which we can understand the similar problem. So if you think about any object, this one for example, as a mapping from the sphere. Okay, meaning at every point on the sphere you map onto an XYZ point on the object, right? And that mapping is just a x as a function of positions on the sphere, y as a function of positions on the sphere, z as a function of positions on the sphere. Just as a red, green, blue image, a color image, is r as a function of x, y, z as a function of x, y, sorry, yeah, x as a function, let me start, say it so, just as r as a function of x, y, g as a function of x, y, and b as a function of x, y. You have three image functions on the flat space x, y, but now we're going to have functions from the sphere. It turns out that there exists a set of orthogonal basis functions from the sphere that are called spherical harmonics. They're basis functions from theta phi, latitude and longitude on the sphere. So functions from theta phi, which are latitude and longitude, to, for example, to positions on a surface of an object, x, y, z positions. And there are functions, basis functions, psi k of theta phi, that you can take any function in x, y, z, or any function, and understand it as mapping from latitude and longitude to these positions. And once you do that, all the stuff that we've talked about works. Okay, so now you're talking about object representations in terms of basis functions that are spherical harmonics. You're not going to have to deal with those in this course. If you take Comp 775, you'll see that spherical harmonic decomposition. But the main point I want to make is that this general notion of dividing things into basis functions and into basis functions that are useful to apply operators on, okay, are, rather general. Okay, okay? Any questions about that? Get rid of this. Best I can. Okay, so now we're going to talk about linear shift invariant operators and how we compute with them. Well, in order to understand them, I want you to understand the idea of there is an image. In one dimension, there's this blue, function, and a weighting function, which need not be positive. Many of the ones we'll be talking about will be positive, but it can have some negative values as well. But we can multiply at every x the weight times the image and integrate, add it all up, and we get this weighted sum of I of x. Okay? So, that's fine. But now we can talk about having the weighting function be centered at some y. Okay? So now, instead of it being centered at the origin, here it's centered at y. That is to say, it's the function w of x minus y. That's the w function, but centered at y. And we get the same thing, w of x, the weighted sum. But now you can do that for every y. We can do it for centering, having the weighting function here, having the weighting function here, having the weighting function here, having the weighted function here, and we get a function of y that's called the convolution of I with the kernel, the convolution kernel, W. Okay? You can think of this weighting function as swinging along here, and at every value that it's centered at, it gives you a new value of J. Okay, so look at this graph here. What we have is an image which is in the form of a rectangle. It's simply 0 up to minus 0.5, and then 1 up to 0.5, and then 0 again. And in this particular example, the weighting function is also the same form. But now the weighting function is moving along, and I think you can see that if I stop this movie at some point, well, let me see if I can stop it. Well, okay. At any given point, as long as there's no overlap between the weighting function centered at y and this gets 0, but as the overlap is the yellow, the overlap becomes maximal when they're fully the same, and then they get smaller. The resulting of that convolution is this triangle function. Right? It goes up linearly from 0 up to the maximum, which is the overlap of the two functions, and it comes down. And so we say, for example, if we talk about rect of x, involved with rect of x gives, we'll call it triangle of x. Okay, so we have an image which happens to be rect and a weighting function which is also that, and we can see that the convolution of the two, of the kernel rect with the image rect, gives us the triangle function. Okay? Well, for images, everything's going to be the same, only x, instead of being one variable, is 2 in a two-dimensional image, or 3 in a three-dimensional image. And so what we have is we have a space, an image, I, and we have some weighting function centered at, okay, so this, those dimensions I'm calling x, and here's a position y, and we're going to have some weighting function in that region, let's say is non-zero, is 0 outside that region. That's some function that is, I haven't drawn, but it might be a Gaussian, for example, bell-shaped curve. And the result is going to be this weighting function, this kernel function, times this image integrated over, be careful, have to integrate also over all the image. Everybody okay with that? Well, it turns out that every shift invariant linear operator can be written as such a convolution. Okay, so in other words, if you have a shift invariant linear operator, then there exists a W, a kernel, that applied by this formula implements that shift invariant linear operator. Okay? More precisely, get the slides back up. More precisely, either a shift invariant operator is either such a convolution, or it's a limit of such convolutions over as the kernel goes to some limit. Okay, we're just going to say convolution is just a kernel. So, what's an example? Well, one example is we might want to do smoothing. In case we want to do smoothing, we'll see that there's good reason that the convolution kernel should be a Gaussian. It has the Gaussian function e to the minus a half x squared over sigma squared times in one in one dimension is an exceptionally good smoothing function. In 2D, it simply turns into that, which is just this function rotated around the axis. All right, so it's a bell-shaped thing. In 3D, likewise, okay, it's highest at 0, and it's spherically symmetric no matter what direction you go from the origin. You get the same cross-sectional function, which is this one-dimensional guy that I had. Okay, so there's an example of a shift invariant linear operator. But what's another example of a shift invariant linear operator? Well, take partial derivative in x. Is it the case that if you shift an image and then take the partial derivative in x and then shift the result back, that that's the same as applying the partial derivative to the original image? Sure enough, that is shift invariant. It's linear. Is it the case that the derivative of the sum of two images is the sum of the two derivative images? Sure enough. Is it the case that if you take an image multiplied by a scalar constant and then take the derivative and then divide back by the scalar constant, you get the same result? Sure enough. Okay. Well, sorry, that was the shift invariant. The question is, if you apply it to a constant time image, is it the constant time derivative image? Sure enough. So you've checked the two things. It works on sums and it works on scalar multiplications. Yeah, if derivative is a shift invariant linear operator, it must be some kernel corresponding to derivative taking. If so, there must be a corresponding set of eigencoefficients of that operation that allow us to apply derivatives in the frequency domain faster than we could apply them in the space domain. Okay? Same thing, and indeed the program that was written for you to use by Alan Lee to compute partial derivatives works exactly that way. It goes into the frequency domain to give you magnitude and the phase. It does the transformation, the appropriate transformation on the magnitude and phase in the frequency domain, changing those coefficients appropriately by frequency term multiplication, coefficient by coefficient multiplication. And then it takes back. And all we have to know is what that function is, so-called transfer function, over on the frequency domain, which is the eigenfunction, the eigen image. After all, this W of x thing is a function of x and y, or in 3D x, y, and z. And so you can think of that as an image too. Right? And so it's an image, just like I is an image, and the result J is an image. Okay, but it's the convolution kernel image. And what we're going to see is that the Fourier transform of W is exactly the eigenvalues we need. So we both understand the image in the frequency domain and the kernel in the frequency domain. We multiply them frequency by frequency together. We get the result, and then we come back. And that's exactly what was going on in the program that you're using for your homework. You will also see that the Gaussian was involved in the program you had in your homework, right? Why Gaussian? And that is because any operator that we do, derivative taking, for example, has to have an aperture, a region over which it is applied. Right? You've been taking math courses. Mathematicians have been teaching you all about the infinitesimal aperture. Right? As if you could apply an operator as epsilon goes to 0. Right? Huh? There's no human operation or any operation in physics that can work on an infinitesimal aperture. It's an idealization. Perfectly good stuff for you to have learned in calculus, but now we're going to say that no. There's always some range of areas over which the derivative taking operates. We'll call that the aperture. And I don't care whether you're measuring with the world's finest ruler or you're applying the computation in an image, there's always an aperture. It may be an aperture size of a pixel, it may be an aperture size of multiple pixels, okay? And that's what the scale is that you getting some experience with in assignment 4 is. It's the size of the aperture over which the derivative taking is applied. Okay? So we're going to be talking about apertures and aperture sizes, but for the time being, let's just talk about convolution. Okay? Any questions so far? Okay. So there are a few theorems that are important to understand. Okay, so the first thing is it's provable that an image convolved with a kernel H is the same as the image thought of as the kernel, the H function thought of as an image, and the I function thought of as a kernel, and that commutative. It doesn't, I convolved with H is the same as H convolved with I. Okay. You just go do that change of variables y to z minus x and you'll see that that works. Okay? Alternatively, since the convolution of I with H is the same in the frequency domain as take the Fourier transform of I and the Fourier transform of H and multiply them, and multiplication is commutative, you can argue it from that point of view. Either way, big deal that it's commutative. It's also associative, meaning if you take the image and convolve it with one kernel and convolve the result with another kernel, you can equivalently take the two kernels and convolve them and then apply that as a kernel to the image, or you can apply one of the other kernel because of the commutativity and associativity to the image, and then you can apply the operators in a separate order, right? First H1, then H2, or then first H2 and then H1. Okay? So, if that's the case, then if, for example, H2 is Gaussian smoothing and H1 accomplishes derivative taking, then this says if you take the derivative of the Gaussian and then convolve it with I, you'll get the same result. Right? You bring together apply linear operators in sequence, we can do that. Or we can take the derivative of the image and then apply the Gaussian smoothing. Okay? Okay, so I showed you the online movie from Wiki. You can also find one at Wolfram and one at Google. And you'll see the same thing of a kernel moving along a moving along X, moving around X. And the point is that we say we take this and we superimpose it on I, we multiply it element by element, position by position, X by X. This is X. And then we do that for every possible Y, and we get a curve. Okay? Another change of variables says that we can rewrite I as Z plus Y and H reflected about the origin. That's H of minus Y. Okay? And we're going to be interested in this reflected kernel as a weighting function as well. Okay, so what are some convolution kernels that we're going to be interested in? Well, we're interested in not blurring images, but we are interested in removing noise in images. And we'll see that if you look at noise in the frequency domain, a very common, okay, so noise is you know, like electrical noise in the camera that you have, or atmospheric noise from an image from space, or all these random effects. And typically the noise property in the frequency domain is what's called white. That is to say, the variance of the noise is a constant, meaning the noise itself at any given instance is some function that varies between like minus 2 sigma and plus 2 sigma or something like that. And on average, over all possible noise functions, the variance is the same. The strength of the noise is the same at every frequency. We decompose this noise function just like any other function in terms of, as an image, in terms of these sinusoids, and we find the A's, which is this function here, or the magnitude of the A's, to be some function that is mean zero over all possible instantiations and has a constant variance for every k, for every frequency, right? But images, because of the fact that they involve some level of blurring, typically have their magnitudes of their coefficients that fall with respect to frequency. Okay, like that. Okay, so that's what I said. The coefficients are quite low at high frequencies. Right? There's high frequency. This guy is A of the frequency. And what happens is that over here, the noise level is, I should really draw this as, something that varies but falls. But the point is that at these low and moderate frequencies, the noise can be very small relative to the signal. So the signal to noise ratio is very good. But at these frequencies over here, the noise is large relative to the signal. That's what you see in the signal is these salt and pepper sort of things that are that the image looks like. Right? It has this random noise in it, and it appears to be at the high frequencies. A lot of levels of detail. It's not that the noise is at the high frequencies. The noise is at all frequencies, but the signal disappears, and all you see at the high frequencies is essentially noise. Okay? So what would you want to do to remove the noise? Well, in this region here that I have here, you'd like to attenuate, multiply the coefficients by small numbers, right? Because then you're throwing away those components in the image that have very poor signal-to-noise ratio, right? That are almost entirely noise. Get rid of the ones that are almost entirely noise. Multiply these coefficients in the frequency domain by small numbers. So we might want to have a kernel on this image after it's been transformed that maybe looks like that. It actually happens at negative frequencies too. I'm just drawing the positive part. Okay, and so Ooh, that kind of looks like a Gaussian that we want to multiply by in the frequency domain in order to remove noise. But wait a second, what are we multiplying by? We're multiplying by the Fourier transform of the kernel. We'll put it another way, the inverse Fourier transform of this transfer function which is applied in the frequency domain. The inverse Fourier transform of that is the kernel, right? The Fourier transform of the kernel is the transfer function. The Fourier transform, inverse Fourier transform of the transfer function is the kernel. But the inverse Fourier transform of a Gaussian is a Gaussian. Okay, there's some mathematics. So another way of saying what we're doing here is we're computationally convolving with another Gaussian so as to lower the amount of noise in the image. So yeah, it blurs, but on the way it has the salutary effect of getting rid of those frequency components that are dominated by noise. Okay. So the Gaussian is going to be particularly important to us, so you need to know the formula for a Gaussian. I wrote it on the board. Here it is in the slide. If m is the dimension, we have an isotropic Gaussian, then it's 1 over sigma root 2 pi all to the mth power times this function e to the minus a half x squared over sigma squared. And in 2 dimensions, it's a function that looks like this. As I said, it's the rotated version of an ordinary bell-shaped curve. In 1D, it's a 2D bell-shaped curve. Or in 3D, it's a 3D curve also, as I described before. Right? Something that's spherically symmetric. We're also going to be interested in weighting equally within a pixel. Why? Because computationally, that's what we're doing when we form images as pixels. We are really not sampling at a point, we're averaging over a pixel, or integrating over a pixel, all the intensities within the pixel. And so we have this function which in 1D is this rect function that I talked about. It turns out we want our convolution kernel to have an integral of 1. So if it goes from minus a half to plus a half, then it's 1 wide, and then we'll want it to be this function w of x, or the function rect of x, to be 1 high. So the area under this thing is 1. But if it's instead going to be delta x wide, then it's going to be one over delta x high. And we subscript this thing by delta x. And now, if we're in 2D, and it goes from minus half delta x in the x direction and in the y direction, then this thing's going to be squared. Okay, fine. The point is we have this definition of this rect function, and it corresponds to simply averaging the image over some region. Well, we want to understand that in the frequency domain, so we need to know the Fourier transform, the sinusoidal decomposition of rect functions. Or we may want to average over frequencies in the frequency domain. So we may apply a rect function, which is a function of nu. Then we're going to need to know the inverse Fourier transform of the rect function, which is the kernel. If we now take the limit as delta x goes to 0, narrower, 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 rect function, always keeping the area 1. So as it gets narrower, it also gets higher, so that the integral under the rect is 1. Or in 2D, we do the same thing. We're going to let the delta x change, go to very smaller and smaller and smaller in both x and y, or in 3D, in all of x, y, and z. We get a kind of function that we, in that limit, that we call the delta function. So if we have an image here, the delta function is, that's right, okay, is a little region of space, little tiny region of space. Things are 0 here, and the height of the function is exactly the right kind of height to make the area, the integral under that 1. That's what delta x is. See that image before? Someone tell me where you've seen it before. An image that has unit application at a point and 0 application everywhere else.
The pixel basis?
Yep. It's just the standard pixel basis. It's just 1 at at a particular location and 0 everywhere else. You've seen that image before. And so we're going to need to understand pixelization in terms of that kernel. So we're going to want to know what the Fourier transform of the delta image is. We're also going to be interested in the H's that a camera applies. Not computationally, but physically. Okay. So there is this delta function, so-called Dirac delta function, after a mathematician named Dirac. And its integral is 1, and its value other than at the position 0 is infinite, but anyway, exactly such that its area cancels out the very narrow area about 0 in which it operates. Okay? And we're now going to be interested, if we have a Dirac delta function at 0, we're going to be interested in the delta function centered at y. And so what happens if we convolve an image with the Dirac delta kernel? Well, this guy is 0 everywhere except at y, and at y it's just the right unit amount of stuff to pull out the value at y. Okay? So it's just the sampler. When you convolve with it, it gives you the intensity sample value at sample point y. Okay, well, if that's the case, this is a convolution. And so this whole sampling business, turning an image into a bunch of pixels, must be a combination of integration across pixels done by a rect, followed by sampling, which is convolution with a delta. Both of those are shift invariant linear operators. And so when we want to talk about sampling, it's going to be really good to think about it in the frequency domain, right? Because we'll understand it better there. It's just a convolution operation. It's actually a cascade of two operations, one which is averaging within the pixel, and the other one of which is sampling the result at the pixel centers. Okay, so that's what we're going to be doing in one dimension. We're going to be sampling at all the pixel positions. That is to say, we're going to have a delta at each pixel center. Okay, and that function, you may not be too surprised, is called the comb function. Right? It's just got a delta function centered at every integer position. And in 2D, anyone want to guess what it's called? Delta function at every xy integer location.
A brush?
A brush! Of course it's a brush. Right. Good going. Okay, so we're going to be interested in, for all these various kernels, we're going to be interested in what's going on in the frequency domain for a particular kernel that we want to talk about in the space domain. And I'm going to very shortly show you this table, which is pretty much all the kernels you'll be concerned about in this course. Okay? And what the kernels are and what their Fourier transforms are, which are the corresponding transfer functions, or if you will, the eigenvalue corresponding to that convolution. Okay? But let's talk about the Fourier transform of a Gaussian. Well, Fourier transform of a Gaussian is a Gaussian, which means if I want to convolve with something in space that looks Gaussian, then there's going to be its Fourier transform, which is going to be now the transfer function. Fourier transform of a Gaussian is a Gaussian. And so we're going to be multiplying by a Gaussian in the frequency domain, frequency by frequency. Right? A Gaussian function of frequency. Derivatives? Well, you want to take a derivative? We need the Fourier transform of the derivative operator. We'll see that the Fourier transform of a derivative operator is simply a linear function in one dimension. As far as the magnitude the term is concerned, it's just multiplying by that function of nu. Okay, that's nu in one dimension. You're going to take a partial derivative in the x direction. You have this nu sub x, and then there's a, wait a second, you should say there's a phase change. Oh, not good enough to tell me what's happening to the magnitudes. You need a phase change. And the answer is phase phase shift, I guess I should say, phase shift equals pi over 2 at all frequencies, except for those special frequencies that don't change phase. The zero frequency k equals 0 and k equals n over 2. But isn't that easy as a way to take a derivative? You go over in the frequency domain, you just go frequency by frequency multiplying by the frequency. Multiplying the result by the frequency in x. And then you change all the phases by pi over 2, and we take the inverse for our transform, and we've done the partial derivative in x. Okay? What about second derivatives? What's the second derivative in terms of first derivatives? If I want to take a function and take its second derivative, I take its first derivative, and then what to get the second derivative? It's the first derivative of that, right? It's the first derivative of the first derivative. It's a cascade of two first derivative operators. Right? And you understand what I mean by cascade, I hope? First, you play one, and then you play the next one on the result. But cascading operators corresponds to multiplication in the frequency domain. And so if this is first derivative in x looked at in the frequency domain, then this squared, this convolved with itself, produces, were you taking advantage that h1 applied to h2 applied to x is h1 convolved with h2, parentheses, all applied to x, and that is a derivative of the derivative. And so we're going to get the square of this thing, which is a function, a quadratic function that looks like that, right? And that's what the second derivative operator is going to look like. It's just multiplying by nu squared. With a phase shift of pi. What's the phase shift of pi? I remind you that of this picture here, where this is the number 1 plus 0i in the frequency in the complex number domain, and this guy is 0 plus 1i, and he has a phase of pi over 2, and this guy over here is minus 1 plus 0i, and it also has a phase shift of pi over 2. So all that's going on with this phase shift is everything's being multiplied by minus 1. Okay? So derivative taking, that's actually what's going on underneath the hood in the program that you were provided on assignment 4. You would that only use first derivatives, right? But had you needed to use second derivatives, and on assignment 5 you will have to use second derivatives, then you don't know how that's going to go. Except now we're going to make you do it. So that under the hood thing that was given to you on assignment 4, we're going to make you have an experience in the frequency domain getting around with all that nasty stuff of, well, the second half is really the negative half, and the complex conjugation means that you have something that appears over here that repeats itself over here, but with complex conjugacy and all that nasty stuff. Sorry about that. That's what you really have to do when you're going to operate in the frequency domain. Once in your life, you're going to need to see how that goes. So assignment 5 is going to require you to do that with second derivative operators. Okay? Well, this derivative thing that I've been talking about, first derivatives, second derivatives in one direction, applies to any derivative. It applies to all directional derivatives. Right? So if you have a derivative, first derivative in some particular direction u, yep, that's shift invariant linear. There must be a kernel associated with it. Is if you have a third derivative, directional, in u1, u2, u3. Yep, shift invariant linear. We can build it in the frequency domain. We can build all those tensor elements that we talked about for any order derivative in the frequency domain. And then any linear combination of them works. So for example, the Laplacian operator is d by dx, d2 by dx squared plus d2 by dy squared in 2D, or d2 by dx squared plus d2 by dy squared plus d2 by dz squared, which is to say the Laplacian on an image is this. But that Laplacian operation is a linear combination of second derivatives x and second derivatives in y, weighted sum of them. That's what I mean by linear combination. And linear combinations of derivatives are also shift invariant linear. And by the way, this guy turns out to be the sum of the second derivatives twice in any u direction together with the second derivatives twice in the perpendicular to u direction. That is to say, it's independent of the orientation, and so it must somehow have a kernel that is circularly symmetric. And we're going to see that that's why it's really good for picking out circular blobs, which is what I said in an early lecture the Laplacian would be good for. Okay? We're going to see an idea called matched filter, where the best thing to pick out of something of a particular shape in an image is to simply use that shape as the kernel. Okay. So, great. We want to be able to take any derivative and to do it in the frequency domain. But as I indicated before, we really don't want to think about derivatives without thinking about aperture. We're going to be talking about derivatives with respect to an aperture. We're going to talk about the size of the aperture as the spatial scale. And a whole section of this course, coming up soon, is going to be thinking about not only positions in images, but also the scale of the operators. Or understanding image, the functions of not only position, but spatial scale. And I've just waved my hands at you and said, we'll see why shortly, but I've said that the Gaussian is the right aperture. It's the aperture function that has exactly the properties that we want an aperture function to have. And it turns out it's uniquely so, would you believe? So, what we want to do is apply this aperture function on the image and then apply the derivative on that. Or, since the order doesn't matter, we can apply the derivative function and then the aperture function. But either way, we're going to be two multiplications. One of them is going to be a multiplication by the Fourier transform of the kernel corresponding to the derivative, and the other one is going to be the Fourier transform of a Gaussian, which is a Gaussian. Okay? Or using this form that I talked about before, where you can talk about the result being H1 convolved with H2 convolved with I. We're going to be more interested in kernels that are the derivative of a Gaussian. Okay, and a kernel that is a derivative of Gaussian is a kernel taken at an aperture size given by the width of the Gaussian sigma, the width sigma of the Gaussian, and the derivative of it. And so what I'm showing you in this picture is in 2D, there's the Gaussian at top. The first derivative of a Gaussian in the x direction is this function like so. So let's just make sure we understand what's going on here. We do some erasing here. Okay, so here's a Gaussian, one dimension. Okay, we'll rotate it later to get 2 dimensions. Its derivative here is 0, right? Way over here, it's basically flat, so the derivative is 0. It's an increasing positive derivative function that at some place here, which by the way turns out to be sigma, this guy gets higher and higher. This guy here gets higher and higher slope until it gets here, and then it comes down, has to come down to 0 by there. And the symmetry tells you that it's going to look like that. It's got a negative derivative on the for the positive x. Okay. So in x, it looks like this function. In y, it's just a Gaussian in y also applied. You can think of a cascade of a Gaussian in x and a Gaussian in y. And so the whole business looks like this. Here's the positive load, here's the negative load as you go in the x direction, but in the y direction, it's just a Gaussian at any given x. Essentially the product of those two. Okay? Well, if you look at the second derivative function, twice in x, it looks like so. Right? It has a big lobe. It's convex downward, which means it has negative second derivative here. Well, it's just the derivative of the derivative. You can see that from here to here, it's got negative. The red function, which is the first derivative, is also negative. And from here to here, it's positive, and here to here, is positive, okay, or tipped over on itself, because I plot here the second derivative twice in x. Right, minus g sub xx, twice the second partial, d2 of g by dx squared. And it looks like that. Cross section in x has got this negative lobe over here, negative lobe over here, and positive lobe in the middle. And in the y direction, still just the Gaussian. Yeah.
So if we think about this combination of operations and as the multiplication of the two transfer functions, and you drew the derivative as increasing in slope y, like I'm just thinking about multiplying the line y equals x with the Gaussian, and you would get something that would be negative and negative x and positive x versus.
Why did I multiply by minus?
Yes.
That's what you're asking?
Mm-hmm.
Well, because later we're going to be interested in applying it to finding bars, and we're going to want to weight the bar by something. If the bar goes, it's 0 and then it goes to something higher and then it comes back down, and it happens so that the crossing direction is x. We're going to want to weight by this positive guy, the guy that's positive in the middle. Okay, so this is, when we get into match filters, we'll see that. But that's basically. I could have drawn g sub xx.
I mean with g sub x, because like right there when you drew the transfer function for the derivative on the right.
Okay, this is not the transfer function; it's the kernel. But let's make. Okay, it's the this is the first derivative of kernel. Okay, but go on.
Okay, I was just thinking when you drew the transfer function for the first derivative, it was the line y equals x. So I think I was just thinking about the Gaussian as the transfer function and not the kernel, which is why I was confused.
Yeah, okay, yeah, indeed, it's easy. I've said a lot here, because we've been going back and forth teaching kernels which are in the space domain, and and where kernels live, and their Fourier transforms, which are the eigen images over there in the frequency domain, and we call those transfer functions, the Fourier transform of kernels. If you want to really get confused, later we're going to talk about kernels applied as convolution in the frequency domain, and then we're going to be worrying about what happens in the space domain. But let's not worry about that right now. Okay, so we got space domain, kernels, frequency domain, transfer functions. And what I've just said is that multiplying by this g sub xx kernel, not minus g sub xx, but just g sub xx, this guy turned over so that it holds water in the middle, is going to be the same in the frequency domain as multiplying by that transfer function. Except we're going to want to do it with a Gaussian aperture. Which means that this function is going to get multiplied, this linear function is going to get multiplied by some Gaussian. Oops, I didn't draw it. It's going to be multiplied by, because you have cascade of Gaussian convolution and this, and so the product of this kernel and the Gaussian kernel is going to be some sort of a function that looks like that, because we multiply in the frequency domain, which is the same as convolution in the space domain, the second derivative operator and the aperture operator. Does that example help?
Yeah, that's what I was asking about, why we got something that looked like that and not like that. But I see now that that's the kernel and that's the transfer
Good.
function.
Good. Any other questions? Okay. And while we're at it, that's what the Laplacian of the Gaussian looks like in the space domain. Or more precisely, the minus of the Laplacian of the Gaussian. It's just sort of the second derivative thing rotated around. People call it the Mexican hat operator. Right? This is in the space domain. And it's the rotation of the second derivative minus second derivative operator. Right. Looks like a Mexican hat. That's okay, so that's what the Laplacian of the Gaussian looks like. Okay, so we're going to talk next time, we're running out of time now, about what's going on when we want to talk about what a camera does, because we're going to be interested in understanding images as starting from a scene and having the camera apply a convolution with its kernel to produce an image. And to produce a digital image, it's going to need to be sampled, and all this stuff is going to be understood in the frequency domain. And then we're going to go on and talk about these basic functions that we've been talking about. Right? We've got the delta functions. We've got the comb function and its generalization, the brush. We have these averaging functions, the rects. We have the Gaussians, which produce our best aperture functions. And we have the derivatives, and one particular weighted sum of derivatives, second derivatives, called the Laplacian. And those are going to be all we're going to be really spending all our time on in this course. And so we're going to be interested then in what the Fourier transform of them is. That is to say, what the sinusoidal coefficients corresponding that you're going to multiply by if you work in the frequency domain. And this table is something you should, print out and carry around in your pocket or pocketbook. Right? This is, you're going to look this up again and again and again and again. Okay? So we're done with today's lecture except for any questions that people might have. Let me briefly summarize. What in this class we've talked about is that shift invariant linear operators can be understood as convolutions with kernels, but they can also be understood as multiplication in the frequency domain by products with transfer functions. And the transfer functions are just the Fourier transform, the coefficients corresponding to the kernels. And then we've talked about a bunch of examples of particular operations that we're going to be interested in, what the kernels are and what the transfer functions are. Okay? Till Thursday. Remind you the assignments due on Thursday. Assignment 4. See ya.